Welcome back, everybody. Today we're going to build off our work with integrating over rectangles and see how we can integrate over more general regions. This makes perfect sense since no matter what our region looks like in the XY plane, we have a function over top. We can ask what the space is, the volume that our graph is bounding. I claim there are two main points to keep in mind here. First, we want to pick a direction to cut in. And this amounts to setting one variable and moving the other. Once we've done that, our limits come from the start and stop instructions for our variable that's moving. And this might sound different than what we've been doing, integrating over rectangles, but I claim it's really the same, and I want to convince you of that before we dive in. So, back when we were integrating over a rectangle, we had two different directions we could cut, either horizontally or vertically. Let's think about vertical cuts right now. This would be where we set x. So we have an x that we've set at, and then we're going to cut vertically. And really this would mean integrating y starting from 2 and moving up to 4. Right? And as soon as we cut through our solid, we get some cross-section that has some area that came from our cut, and we could compute that. And we would then go through and get a cross-section at each and every x along the way here. So over here at this x, we would start y at 2, move it up to 4, get our cross-section. At this x over here, start y at 2, move it up to 4, and get our cross-section. In each case, we are moving y from 2 to 4 always. And I claim because of that, that's what allows us to set up our integral where we are moving y to start. We're always moving y from 2 to 4. All right, so this came from how we were moving y, always from 2 to 4. And then the outside limits for x were then 1 to 5. And I claim that that came from the fact that we were always cutting using x's starting at 1 and then up through 5. And in general, the outside integral here is answering the question, what x's do we do this for? And again, this outside x, we reset x and we moved y. Now, this exact same game is what we can use to think about how we can set up our integral over a more general region. Once again, let's think about the same cutting strategy of setting x and moving y over here. Now, if we set x at these different values, and we get our vertical cuts. Here we're moving y from the bottom up to the top. And over here on the right at this x, starting y at the bottom, moving it to the top. At this x, starting y at the bottom, moving to the top. What's interesting here is that in this case, we're not always starting at the same number and stopping at the same number. Right? In the middle, we're maybe starting around 3, whereas over on the right, we're starting at like 3.5 or something. And our starting y values change as well. So our start-stop instructions depend on x. However, our starting instructions always come from this line. All right? And so our starting y values always come from that line's formula. They depend on x, and so it's some function of x, some b of x. And here, since I've actually drawn this as a line, we can actually get a formula for it. It goes over to, up to, so it has a slope 1, and it would actually connect up at positive 1 on the y-axis. So here, this formula would be y equals x plus 1. Okay. This is telling us the y value to start at, depending on what x we choose. Now, the stopping instruction for y, again, different y's, but always coming from this top function. So here we'd have some t of x top function that we'd stop at, and we're always starting at the bottom function, the line, and stopping at the top. And so those become our limits of integration for y. Y from b of x to t of x. And that's telling us how we move y. And here, once again, this b of x we actually know from our picture. It's x plus 1. And so what's interesting is that in more general regions, we can actually have functions as our limits of integration, as we see here. Now, for the outer limits, once again, the question is, what x's are we cutting like this for? And we're starting to cut over here at x equals 1 and stopping to cut over here at the end at x equals 3. So those become our start-stop instructions for x, telling us what x's we cut at, the x's we set. Now, just like in our rectangular situation, we're perfectly free to cut in the other direction. We can make horizontal cuts, which is setting y moving x. Let's see how that plays out in our more general ice cream shaped region here. So here let's think about setting y moving x. And so at this point, setting y is we're picking what y we want to start at. Maybe we'll set y here. And we're going to move x. I don't like the color. I'm deciding at this moment. If we set y here, we're going to make a horizontal cut, starting x on this left-hand side, moving it to the right. If we set y maybe a little bit further down, still starting x at 1, but stopping it at a different x value, but still on the line here. All right, so once again, our stopping value for x is going to depend on what y we chose. And so here we have some function of y, I'll call it r of y, that tells us what x we want to stop at. So r of y since we're on the right. Now if we choose a y that's a little bit further up, again we're starting x at 1, stopping it on the line. But if we go high enough up here, now we are starting x not on this solid line on the left at 1, but actually on this curve. And we're stopping ourselves at this curve over on the other side. And so here, right past this kind of connection point up top, we actually have different start-stop instructions. Our instructions change from this kind of triangle piece below, and so we actually would need two integrals. One for the bottom triangle piece and one for this curvy top piece in order to set this up fully in this order. So at this point we'd be like, gross, maybe I'll just try to go with the first option. But for fun and good practice, let's see what this looks like to set it up fully in this direction. One last note, up in this top piece, we have kind of this left-hand side that we're starting at and this right-hand side that we're stopping at. Both of these, we need to know what x to use. And so these will be functions of y. So I'll use capital L for the left-hand side and capital R for the right-hand side, right? Because the x that we're starting and stop at will depend on y. Okay, now we're going to have two integrals to set this up. We are setting y, moving x, so dx is on the inside, dy is on the outside. And as always, we're just integrating our green function, whatever that happens to be. So for this first triangular piece, let's do the triangular piece first. We're always starting x at 1 on the left, and we're stopping x on this line on the right-hand side, which we can actually grab the formula from. We know the equation for that line. We need to know what x that tells us about. And so here, we can just solve our equation for x and get x is what? Y minus 1. And so that's what would go up top here, starting x at 1 and stopping x at y minus 1. Right? That's what our r of y function actually is. Now the outside limits are again asking us what y's do we do this for? And this triangle portion starts at 2, and we cut until 4. So those are the y's that we use. Now for the curvy section up top, we're always starting x on this left-hand curve, stopping it on the right. So it'd be x equals L of y up to R of y, whatever those functions happen to be. And what y's are we using? Y's from 4 up to 5. That's what we're cutting at. So y equals 4 up to 5. And so here, notice a very stark difference between what it's like to change the order of integration from our rectangular situation. If we wanted to switch the order there, we would just flip the two integrals and we'd go about our way integrating. But in more general regions, we have a much more interesting and complex situation going on. If we want to change the order of integration, we need to use the picture, make our cuts, figure out what our start-stop instructions are, and let that dictate how we set up our integral. And just like we saw here, we can definitely switch the order of integration, but things can change. In particular, the limits of integration change from what they were, and even the number of integrals. They at least can change. They don't have to, but they can change, like in our situation here. We had one integral in the first direction of cuts, and we needed 2 in the second. Let's see how this plays out with a specific example. So here we have an integral of this boring function y. This is our f of x, y, giving us our green hill on top of some region. And in this region D, we're told is bounded by this line and this sideways parabola. And so we need to figure out our limits of integration so that we can eventually compute this thing. In order to figure out the limits of integration, we need the picture. It all comes from the picture, from drawing our cuts and thinking about start-stop instructions. So our line looks something like this. There's y equals x minus 2, and our sideways parabola looks something like this. There is x equals y squared, and so here is our region D that we are integrating over. Again, the idea is that standing over top of your screen that you're looking at right now, we have our green hillside, and we're looking at the volume that's standing over top or underneath this region D. Okay, so we have two directions to cut. One where we set Y, move X, one where we set X and move Y. In just a second, pause the video and see if you can draw in your cuts, figure out what your start-stop instructions are, and set up the integral in both of these ways. Once you've done that, pick the one you like best and compute it. Pause the video and see what you can do. All right, so let's talk through this. In this first option, setting Y and moving X. So here, that looks like the following. So setting Y, moving X, we are making our cuts at our different Y values. And if we set our Y, we're moving X from the left-hand side to the right. And as I draw this, once again, I don't like the color. Let me use pink maybe. So moving X from the left to the right. If we set Y up here, make our horizontal cut. Moving Y from the left, X from the left to the right. And down here, moving X from the left to the right. And what we see actually is in this setup, we're always starting X on this parabola and stopping X on the line. So we have consistent start-stop instructions. And now we can set up our integral, and we'll only need one. So we have our function y hanging out, and we are moving x to start, and we're always starting x on the parabola and stopping it on the line. I kind of like writing in the words sometimes, but now we can fill in what we know these formulas are. Our parabola formula is y squared. And our formula for the line is right up here, but this is telling us what y equals. We need to know what this tells us about x. So we just need to solve this for x real quick. Y plus 2. So that would be the formula up above. So we're always starting x on the parabola, stopping at the line. What about y? Well, what y's are we doing this for? Well, we need to know the this bottom y coming from our point of intersection here, and the top y coming from this point of intersection over here. And so to intersect those curves, we just need to let these equations talk to each other, kind of sub them in. And if we kind of feed in y squared for x there, we get the following quadratic equation. We can toss the y over. And this does, in fact, factor cleanly. And so the y's are 2 and minus 1. And that looks pretty reasonable from our picture. Those are the y's that we're using, the ones between those. And so those become our limits of integration. And we've set up our integral in this order. In the other order, we're going to have some different cuts. Maybe I'll draw those in purple. So for option 2, now we're setting x, moving y. So we're setting x at these different x's. And at this first one, maybe let me, moving y. Right, taking vertical cuts, all of these are going to be vertical cuts at all of these x's. We can just toss those in real quick and just see what y is up to. Y is starting at the line, stopping at the parabola, starting at the line, stopping at the parabola. But over here, something different. Over here, we're starting on the bottom side of the parabola and stopping at the top side of the parabola. So here, once again, we have kind of two different sets of instructions, and so we would need two integrals in this order. So we can set it up. In the order that we're doing, this is setting x and moving y. So y is on the inside, x is on the outside. We are integrating our function, which we know is y, so we can write that in. All right. And we're always moving, let's say we got two chunks. Let's maybe just go left to right here. So this chunk on the left, moving y from the bottom side of the parabola to the top side, well, we need to take our parabola's equation and let it tell us what that means for y. So solve it for y. And careful, if we square root both sides, we do need plus or minus root x. That's giving us the positive side of the parabola and the negative side of the parabola. And so here are our start instructions for y. We're starting it on the negative side of the parabola and moving it up to the top. And what x's do we do that for? Well, the first x is 0, and we can see that from the picture. We need to know what x this intersection happens at, and we can just feed our y values for the intersection into our formula for x here. I'm just going to add 2 to them, so that's going to be, it looks like 1 and 4 are the x's of our intersection points. And so this first x equals 1, that tells us the stopping x for that first chunk. So this is going to be x from 0 to 1. And the next chunk we're cutting from 1 to 4 at our x's. And for each one of those, we are moving y from the line to the top of the parabola. And again, the line here, that equation is x minus 2. And the parabola equation for the top is root x. And with that, we've set this up. And I think we can all agree that this first option with one integral, that seems a little bit more manageable to integrate with. Go ahead, if you haven't already, see if you can integrate that and get the result. And we'll talk about this next time in class.